The farthest individual star ever seen, courtesy of the Hubble Space Telescope. Welcome back to Techstination. I'm Fred Fishkin, and joining us are NASA astrophysicist Dr. Padi Boyd, chief of the Exoplanets and Stellar Astrophysics Laboratory. Thank you for taking the time with us, Padi.
Oh, it's my pleasure. I'm really excited to be here to talk about such an exciting result with Hubble.
And also with us is Bob Vanderbei, a professor at Princeton University with a passion for astronomy and especially astrophotography, co-author of Sizing Up the Universe and the upcoming Welcome to the Universe in 3D. Great to see you again, Bob.
Great to be here. Thanks.
Well, the Hubble Space Telescope has been amazing us for more than 30 years, and we'll keep at it even as the new James Webb Space Telescope comes into service. And just announced is a record-breaking Hubble discovery. Tell us about the news, Padi.
So this is a record. It is the farthest single star that we have ever been able to observe. And the light from this single star left that object when the universe was about 1 billion years old, maybe even younger. Right now we're at 13.8 or so billion years old. So we're really looking at a baby picture of a star from the very early universe. And the way that we were able to do this with Hubble is so fascinating. You know, like Hubble has been up there for over 30 years, as you said. We're really pushing it to the peak of its capabilities by using a natural lens out there in the universe. When you have a cluster of galaxy with hundreds of trillions of masses of the sun, it actually bends the light and it makes its own lens, and it can amplify, magnify, and distort very distant objects behind it. And so that's how we're seeing this farthest star.
Bob, I'm going to let you jump in here. Your reaction to the news that came out today?
I'm totally excited about it, and I can't wait to see JWST pictures of it. And I did have a question for you. So gravitational lensing requires things to be properly aligned, and there's lots of stories of things moving a little bit, and then the gravitational lensing can stop. So I'm wondering, how long has this been going, do you think, and how long will it be still observable?
That's an awesome question. You're absolutely right. Gravitational lensing is not something that's fixed in the universe. The universe itself is dynamic. We know that the universe has expanded, is accelerating. And so things where they appear to be, say, 5 billion years ago or 12.9 billion years ago have moved since then. So we really are taking advantage of these chance alignments. And there's an amazing program that Hubble has continued to initiate called a treasury program, the Hubble Treasury Program, called RELIX, where we actually are looking at dozens of these clusters of galaxies and exposing them in multiple color filters for a long time so that we can start to see those objects behind it as they, peer out of the mist there, so to speak. So for this particular star, in this particular ancient galaxy, we are very lucky that the chance alignment has happened. But the things that are so cool about it is that those motions are slow enough that over, say, about the last 3 or 4 years that this program has been revisiting that area, this star has been basically bang on what we call the caustic in that mathematical model, the place where the magnification is absolutely the highest that it can be. So we're lucky enough that we're seeing about 1,000 or more times magnification of this single star. It could last for another dozen or so years. So plenty of time for Hubble to go back, plenty of time for James Webb to get on there and see what's really going on under there.
And the simple explanation would be this is what allowed you to see it? Gravitational lensing?
Absolutely. Yes. So the clusters are so massive that they magnify, amplify, distort the objects behind them. We would have no way of seeing them without that magnification lens of the galaxies themselves and their mass. And also we observe them in the reddest filters, the infrared filters on Hubble, to really push back into what's been redshifted out of our visible range. So both of those components together, that Hubble can see in the infrared and that the lens itself is magnifying and amplifying what's behind it, has made this observation, this discovery possible.
So is this image that we're seeing, is it a stack of images taken over these couple of years that you said that Hubble's been pointing at this cluster of galaxies, or do we have multiple images that all show this star?
So it's a little bit of both. If you looked at the images that were released today, where you see that, the arc that's very red, and very elongated. It's actually stacked on top of images at other wavelengths. So we took many wavelengths in 2 different instruments on Hubble to get this panchromatic look. And that red that you're seeing is basically indicating to you that you don't see the arc in the visible filters. You really need to go into those redder wavelengths to see it. But there also are epochs, different observation times when we go back and look at the same clusters again. So you can also do like the time variability of the star to show that it's not just sort of like a chance event that happened in one image, that it's been there consistently for the last 3 or 4 years.
Interesting.
Tell us about the name.
Earendel. So that means morning star or first light. And so why that name was chosen, it's a nickname for the star. It was chosen by the discoverer. So the team of folks that put these observation requests in is led by Dan Coe, and his graduate student Brian Welch has been analyzing the data and came to the conclusion that this is a single star. And so when they realized that it was like this record-breaking farthest star that we've ever seen by far, really breaking the records, they came up with this really beautiful nickname, Earendel, meaning basically that, the first light, the morning star, the sunrise of the history of the universe. Because when we look back that far into time, the look back time, we're looking at a universe that's very different than the universe we see around us today. The heavier elements that make up everything around us, including us and our computers, those all were, churned in the furnaces of stars that were born, lived, and then died in supernova explosions and spewed out these heavier elements into, the surroundings, the other stars picking them up as they were evolving. This star is from well before most of that happened. So it really is like the dawn of star formation, the dawn of getting those heavier elements out into the universe. And I think it's a beautiful nickname, given all the symbolism of where it really is and what it can tell us about the very earliest days of our universe.
Bob?
And it's a very large, massive star. So when it gets old, is it going to become a black hole?
So you're right. I mean, so a lot of this is based on a model that is dependent on the Hubble data that we have as of today. So one of the most exciting things about this object is that it is one of the objects that the James Webb Space Telescope will take a look at in its first year of science operations, and we'll have a tremendous amount more data on there. So when we have the James Webb data, we'll be able to get a much better estimate of its true mass. But even with what we can tell today, just from the images we have from Hubble, we can ascertain that star is very massive. So compared to one of the stars that you can see with your naked eye, in our Milky Way, it would definitely be on the most massive end of the spectrum. So we're talking like 50 solar masses, maybe even 100. Those are very massive stars. They have extremely short lifetimes. They live maybe 1 million years before they evolve. And absolutely something in our local universe with a mass like that would be expected to collapse into a black hole after a supernova explosion. And that's a pretty good model for everything we see around us today. We're certainly assuming that that's what would happen in the early universe as well. But one of the coolest questions left to answer for James Webb is this, the birth of black holes and the birth of galaxies, the first supermassive black holes that we find in the centers of galaxies, and the galaxies themselves. Which came first, the chicken or the egg? Is it a bunch of massive stars like that in the early universe that do go supernova and then form these big black holes? We're waiting for James Webb to really tell us the answer to that story.
It'll be really awesome. I can't wait for the James Webb images to start appearing. I mean, it's a lot bigger than Hubble, and and it's in the red, so it's perfect in every respect for this kind of research.
And
exactly
the whole process of bringing it online to start sending images back, that's been going pretty well, hasn't it?
Everyone in the astronomical community that's either involved in that process right now or is just peering in from the edges is extremely excited about how well it's going. About a week ago, the James Webb Space Telescope project team released their final alignment images and results, and the mirror is performing as well as the best estimates we're expecting, and possibly even a little bit better. So everything's looking great for JWST. We just need those instruments to cool down to their final operational temperature, which is very, very cold, and then start to calibrate and do their own instrument alignments. And we just can't wait till the data starts rolling in. Even those test images, you can see galaxies in the background that have no analogs in observations today because they're so faint and so red.
And how will these two telescopes work together?
So that's a great question. And that's another thing that we're very excited about. Hubble is still at the peak of its capabilities. It's a giant mirror in space. And even though it's 30 years old, it has been serviced by astronauts 5 times. And the last time the astronauts put their hands on the telescope, they left it with updated instruments, updated computer systems, power systems, and still going strong. So we expect Hubble will be able to operate, well into this decade. And hopefully the engineers can keep it going even longer. And so what Hubble does is it observes in the ultraviolet and the visible and a little bit of the infrared. What Webb will do is really pull that far into the infrared, near infrared and the mid infrared. And so when Hubble and Webb are operating together, we'll have this beautiful panchromatic view of objects, not only much better visible objects than we could ever get, with our eyes or the ground-based telescopes that are in use, but also going into the ultraviolet, going into the infrared, things that our eyes can't see, things that the atmosphere effectively blocks. It's going to be groundbreaking, game-changing for when we can use both these telescopes together to investigate something like this star, like Earendel, one of the earliest stars that we can see.
So Hubble's been going for 30 years. And so it just makes me wonder, given the technological advancements that have happened over 30 years, has anybody discussed the possibility of sending up a rocket, attaching it to Hubble, and sending it out to Lagrange point L2? Or is that just too weird?
Actually, there's all kinds of ideas that are being discussed. There are a lot of people who spent their careers making Hubble as good as it can be. They also work in things like robotic servicing. So, there are all kinds of options that people can talk about. Many of them are theoretical at this moment in time. And then you've got the discussion about what would be the most effective use of an enhanced telescope? Does it make sense to send it to L2, which is that location 4 times further than the moon, where things are very cold? That's ideal for an infrared telescope. Not clear that you'd get a big bang for the buck for Hubble, maybe. But the other issue is how much would it cost? And is there the ability to launch something that's got next generation instruments, next generation computers, power systems for about the same price to get either equal or better science? So those are the kind of conversations that the community does engage in from time to time. Right now there's not an approved program to service Hubble in any way, but there's certainly a lot of people that would love to see the telescope continue as long as it can.
Yeah, and it's interesting that you point out that because it's not infrared, it doesn't matter so much. As long as you're above the atmosphere, low Earth orbit is good enough. And
well, there are certain features in low Earth orbit that make it difficult because we are eclipsed by the planet. The planet Earth gets in our way once every 90-minute orbit. But we also all of our data process, the data coming down from the telescope to the ground, getting processed is all dependent on how we communicate with that observatory where it is right now.
The simple explanation for our audience, maybe from both of you, for us lay people, how do we know something is 12.9 billion years old, this image that we're seeing?
So what we know is that the light that came from it is consistent with 12.9 billion years ago. So like we were saying, the universe is dynamic. So, things have moved since that time. And the way you get that from the Hubble program is that you look at the object, you take basically photographs in different filters. And the galaxy itself has a redshift. And that redshift comes about due to the features in the galactic spectrum. And at some point in time, the light of a galaxy all drops out. And where you see that light dropping out can actually tell you where the redshift is, like which filter you see it dropping out gives you a sense of that redshift. So the distance that we have right now for the object is called a photometric redshift, and it's all based on these broadband colors and where we see the galaxy and where we don't. But JWST will be able to pin that down with incredible precision compared to what we know now.
I mean, for those who aren't astronomers, if you get in your car or if you're standing on the street and a car's coming at you and honks its horn, it's higher pitched because it's coming at you and it's compressing the wave, and so it's higher frequency. Whereas when the car goes past you, it sounds deeper sounding. And the same thing happens with light. If a ball of light was coming really, really fast at you, which would be scary, it would be bluer. And if it's going away from you, it's redder. And so, and because the universe is expanding from the Big Bang, things that are further away are actually, we're moving apart faster. And so it's a question of measuring the speed and interpreting that as a distance. And that's really what all of this is about. How do we measure how far away it is? We can't go there, but we can measure how fast it's moving.
Exactly.
Terrific. Well, Bob and Patty, thank you so much for spending time with us. Really an exciting day. Congratulations.
This is really exciting.
Thank you. My pleasure. Bye-bye.